So a funny thing happened. I started explaining this. I wrote this very nicely. I started explaining this, and I reached until this point. Then I realized the video was not recorded. So I, I really don't think I can write all this stuff again. So I'll just explain it to you very nicely, slowly, um, through the written parts. Please, this is my apology. I want to extend my apology. Please, I hope you understand. I know, I'm a fool, but that's how it is. So I'll explain it to you very nicely. So one of the concepts that I'm not going in depth is called as the D'Alembert's principle. So I want you to take this. This is the formula that's given by D'Alembert's principle. So this is basically the D'Alembert's principle. This summation over Fi vector minus Pi dot. Pi dot is again a force dot delta R vector I is equal to 0. So what does D'Alembert's principle basically say? It's a mathematical, this is a mathematical representation of D'Alembert's principle. So in this equation, all the forces, this Fi, are applied forces, alright? The forces of constraint do not appear in this equation. So this is one of the reasons why we use D'Alembert's principle in order to derive the Lagrange's equation. So I hope you won't mind me skipping this because it's not a waste of time, but there are a lot of concepts which are not necessary as of now. So you can just focus on what you have in your syllabi and just go your nice marks rather than pondering, because now you are on the edge. It's either yes or no. If it's either passing with good grades or just getting a KD. So yeah, let's start with it. So okay, so this is the principle, D'Alembert's principle that I'm going to use in order to derive the Lagrange's equation. So just take this as a lemma, take this as a granted for now. So what we do is we state the D'Alembert's principle. Okay, this is the mathematical statement of D'Alembert's principle. Just keep that in mind. So in our earlier representation, in our earlier classes, we said we have a k holonomic constraints, which is given by 3n minus k is equal to small n. We said we talked about the degrees of freedom, right? The configuration space and so on, right? So in that we said we have a k holonomic constraints, and this 3n minus k is equal to n gives us the representation. So I can use the generalized coordinates as stated over here. So this is qi is equal to q. You don't actually need qi, just state the q. So it's a general q which has all the q1, q2, up to qn. So now we do a transformation of this q as we did it before. If you remember the configuration space, so if you don't, just check that video or just check your notes. So we do a transformations from Ri vector to Ri, is possibly a vector equal to Ri vector, which is a function of this generalized coordinates and also possibly time, because I'm stating it as an holonomic constraint. So this is my transformation equation where my Ri depends on generalized coordinates, this generalized coordinates, and possibly time. So what I do is I do a time derivative of this particular Ri. So if I do a time derivative of this particular, say this is of a displacement, so this will give us the velocity. So velocity is represented by these three terms. So these are three different representations of velocity. Vi denotes the velocity, dr vector of I upon dt will represent the velocity, and Ri dot represents the velocity. So this is Leibniz notation, this is Newtonian notation, and this is just the usual notation that we use. So what we can construct, see, Ri is a function of generalized coordinates and as well as time. So there will be two differential equation, one corresponding to time and one corresponding to generalized coordinates. So the one corresponding to time is given by this. So what we can do is we have to introduce I mean, we have to emphasize this fact. As a result, we try to do this where we get the partial differential equation of this form. So this is possibly how the velocity is represented. So now what we do is we just keep this equation aside for a moment. But what I want to do is this function, they are also the functions of generalized velocities. I mean, see, whenever I say something is a function of this, that means it can get differentiated with respect to that particular variable. So if Ri is a function of q and t, that means there exists a partial differential equation under which my Ri can be partially differentiated, because there are two possible variables, partially differentiated with respect to this particular variable, and Ri can be partially derivated with respect to this particular variable. So that's how we interpret. Now possibly my velocity is also, I mean, they are also the functions of generalized velocity. So what I'll do is I'll take this and differentiate with respect to that particular variable, which are generalized velocities. So dri dot upon dqi dot, which give me this particular representation over here, which is partial differential equation of Ri vector upon d dou qj. So dou, I indicate this as dou. Some people indicate as dou, but I know it just varies from people to people, so I call it dou, whatever. What I'll do is I'll take this equation and I write it in this form, this equation, and what I do is I just use this over here, so that I'll get a representation, the coordinate, not just a coordinate representation, but a particular identity. This is my identity. This is one of the identities I kept aside. Now I want to derive my second identity. That's why I'm going to use this equation. I've done nothing. I just restated this equation. Now what I'm going to do is, now this dr dot can be represented by this particular form, which is given by this. So what I do is I simply multiply throughout by the operator dou by dou qj. This is one of the particular operator that I choose to operate, because possibly it depends on generalized coordinates. So as a result, I want to emphasize that result as an identity. So as a result, I'll just so I'll just use this particular fact multiplied throughout by the operator dou by dou qj. So I take this, so this can be represented by this. I keep this aside. Now this becomes my partial derivative. So dou ri vector upon dou qj, the whole multiplied by this particular or is operated by this particular operator, which is d by dt. This is not partial differential equation, because see here, it does not have a partial differential equation. See, the partial differential equation comes into picture only when your function when a particular vector is a function of two or more variables. In this case, it's two variables and possibly more by generalized velocities. So we take that into account. So what we do is, it's simple algebra. So we divide this, we multiply throughout by this operator, we get this particular equation. Now, if you notice, I did nothing, I just multiplied this equation, I've done nothing. So if you see this is the, I just took it as qk, just to differentiate. It is very much different by dou qj. So dou qj, and here we have dou qj. So it represents a particular dummy indices. So as a result, I am not sure whether the j and k are equal. So in order to just emphasize mathematically, I'm just using it as k, just to make sure that I'm not particular about any particular scenario in this type of derivation. So I take dou by dou qj as common. Whatever left inside in this parenthesis is denoted by this equation. As I said, I, j, k are just the dummy indices. So what I do is, this parenthesis is actually equal to this, right? Is actually equal to the velocity vector. As a result, I write this in this form. I get this. I can also write this as in this, say, the Leibniz notation, just not to confuse you, d by dt. Also, writing in Leibniz notation. Okay, this is the same, just writing the velocity as r dot. Now I'm going to emphasize. So this is my second identity, right? So now what I'm going to do is I can also define a term which is called as the virtual displacement. So virtual displacement actually comes before the limits principle. So it's the hierarchy goes like this. We describe a virtual system. What is the virtual? Then we state about what's called as the virtual displacement. Then we state what's called as the virtual work. Then we move on to the D'Alembert principle. So I'm just going to skip that part because that's really unnecessary, and that will just add two videos onto the portfolio, which I really don't want because I want to scare you guys. So moving on to the derivation. So this is kind of a lemma. It's called as a virtual displacement. This is simple. This is nothing but just a simple derivative trick or something. So if I state my delta ri vector, which is the virtual displacement, denotes the virtual displacement, I get some dow r vector I. So this is how both the variables are same. It's qj, but one is in partial derivative form and other is in delta form. So this particular form of equation is called as the virtual displacement. Now there are two terms in D'Alembert's principle. So if you know, there are two terms. One term, let me go back. So one term is this. If you see, there are two terms. One term this is one term, and the second term is, regardless of the minus sign, dot represent that it's a force. This is my second term. So what I do is I take the first term and I emphasize on that, and similarly I'll take the second term and emphasize on that. So we get two equations, one belonging to first term, other belonging to second term. Then I'll combine that into the principle, D'Alembert's principle, and I further solve to get what's called as the Lagrange's equation. This is just one of the ways. There are two other ways in which we can do it, but I'm just sticking to the basic form. So the first term is this, and the first term is this, as I emphasized just in the back page. So I can, if I see, this is delta Ri. So delta Ri represents my virtual displacement. I just now explained you what the virtual displacement is. So I use this I use this equation, I substitute this equation onto this. So I'll get this. So I'll get this particular quantity times delta qj. This is the delta qj is here, the delta qj is here. But what I do is, whatever the term in my parenthesis, I define the term in my parenthesis as capital Qj, which is just given as the generalized force. I have no interest in emphasizing on the depths of the generalized force because that will again lead to more videos. So just stick to the basic. Thus we can write this. So I define this quantity. Now I'm going to substitute this quantity over here. That's all. So I get this equation. So thus my first equation in the D'Alembert's principle is taken care of. Now my task is to explain how I get the second term. So my second term is usually the momentum dot delta Ri vector. So I just what I do is I just use the definition of momentum, which is m Ri dot nothing but m times v. So I'm just writing in the Leibniz notation so that I can keep everything in terms of Ri, so it can be easy for me to understand what to do next. So what I do is I'll just take this equation, and my mi is constant, so it possibly comes out of this derivative, and as a result my the derivative on velocity is nothing but acceleration, and acceleration is indicated in terms of Leibniz notation is this. So again I use the definition of the virtual displacement. My delta Ri vector has this particular value, so I use this particular value over here, and I get the summation and on one side. So I have two summations, summation that goes for I and summation that goes for j. But actually when it comes to the high level, there is something called Einstein's summation convention. We don't need to use summation, but at this point I have to use it, but that's alright. So this particular equation can take this particular form. Yeah, so this particular equation can take this particular form. So this particular form, let me explain what this particular form is. This is nothing but just a trick on the variables, the differentiable trick that we have used in this kinds of variables. Again, you don't need to emphasize on this much more. You can just remember it, you can just state it what is what. So just take a moment, pause, and just look at the equation, and also look at this equation, how it came, so that you can have an idea of what to do next. Now, what I do is, this is my first term, this is my second term. This particular term can be replaced by my first identity, as I just derived over the last page, and this particular identity can be replaced by this identity. You see? So what I do is, after replacing, I'll get an equation which is given by this. This is nothing, I have just substituted both the equation onto this. So what I get is, from 1 I'll get this equation which states that my dotted term, the partial differential of the r vector I dot upon dow q dot j, which is equal to dow of partial differential of ri vector upon dow qj. This is one of the equations that we will use in order to simplify our fact. After simplifying this, after using this particular equation, we get an equation which becomes like something, which shows something like this. See, I know I'm explaining in the air, because see, it's honestly to speak, in order to study this, you need to have a strong mathematical as well as strong mechanical background, and I'm afraid you audience don't have that background. As a result, I need to explain it in air. So frankly speaking, if it comes in exam, just copy. I know it's the worst advice as a teacher, as a mentor, I can give it to you, but I see no other option. But I know it's unethical for me to tell this, but that's how it goes. Of course, I'm not going to do it. So the second fact is, I have used this equation, and after simplifying this equation, I'll get this equation, which is nothing but mere the substitutions of all the elements that I just showed it to you. Now, again, what I do is, I take the time derivative outside this parenthesis, this particular parenthesis, the square parenthesis. And what I do is, I'll just take dow q dot ij outside. So this becomes a square term. So in order to, just a second. Yeah. So in order to compensate, I have to multiply it by half. So this, if something goes inside the derivative, it becomes square, then I need to compensate that by half. This is the standard trick that we use in the differential equation in the semester 4. Now, so what I do is, I'll do the same thing over here, but I don't have time derivative on this particular equation, this particular term. So I take delta dou by dou qj outside, and I have this particular representation. Thus, I define a quantity called kinetic energy represented by T. It's no more K as we used to do it. In Newtonian mechanics, it's not Ke anymore. Learn to write this equation in terms of T, because this is one of the standard equation that you will see throughout your career in physics. T represents kinetic energy, and kinetic energy have different forms, as we might see in the ongoing lectures. So one of the representation of T goes like this. As a result, I will have this equation where I substituted this as T and this as T. As a result, I get this equation. This is nothing but equal to the second term of the D'Alembert's principle, because that's exactly what I was expanding. So after expansion, I get this equation. It's a beautiful equation to say. Thus, putting all together, I mean this particular term, the second term and the first term. Okay, and the first term. Where's the first term? Yeah, this is the first term. I will substituting this term, not this. Substituting this term and this term in the D'Alembert's principle. In D'Alembert's principle, I'll get an equation like this. You can check it out, or you can just see when I give it. When I upload the notes, you can just see. This is nothing but the same equation. Now the term in this parenthesis must be true for all delta qj, because frankly speaking, whenever my delta qj cannot be equal to 0, because if I set delta qj equal to 0, I know this is one of the worst analogy that I'm giving, but it also makes sense. If I set my delta qj equal to 0, then all the problems that we worked till now, all the equation that we got was based on delta qj, delta ri, so it will become meaningless. So this equation itself will become meaningless. As a result, what I do is I'll just set this term, the square parenthesis equal to 0, and I can take my delta qj, which is in minus sign over there, onto that side, and I get an equation for generalized force in the form of differential kinetic energy. This is nothing but another representation of the so-called generalized force, because we define qj as generalized force, remember? So this is nothing but another representation of the generalized force. So if you see the nature of this equation, it's a second order differential equation, and it is viable to you from the semester 4, because you had the basic course on differential equation, so I don't see any problem over here. Just bear with me for 5 minutes, we will get to the equation straight. Now, what I do is, I take a conservative system. I'll have a holonomic constraint, because we started with having a k holonomic constraints, right? We started with k holonomic constraint, and now what we have in our hand is a k holonomic constraint equation, and further I take it as a conservative system. What happens in a conservative system? If you remember from the center force motion, the forces can be derivable from a potential energy. That what it means. The work then can be negligibly zero and blah blah shit. There are tons of definition that you can find, but one of the definition that we physicists like to use is the potential. The forces can be derivable from the potential. So I define a force in this particular form. It is definable because I can define it, because my force is conservative system. So when if I set my force equal to in this form, I know my Fi is also being represented in the generalized force. See? So I substitute my Fi, the value of this Fi, on this generalized force, and I'll obtain an equation which looks something like this. This is not velocity anymore, this is potential. See, how you can differentiate it, not differentiate mathematically, but how you can see the difference is, this is V, and that is curly V. Curly V is what I use to represent velocity. Where is it? Where is it? Okay, oh yeah. You see, it's curly V. Don't confuse yourself. Okay, so we have this kind of we have an equation for Qj. Now what I can do is I can take I can set it as an independent to Qj, which is independent. I'm not setting it. My force only belongs to R, or say in this case J, generalized coordinates. If you remember classical central force motion, it might be visible to you that a force we took a special condition because for conservative system our force or potential only depends on the coordinates or R, a distance from the source. Here in our classical mechanics it just depends only on the generalized coordinates. So that means my V is independent of Qj. That is, V is only a function of Qj. So as a result, my capital Qj, my generalized force, turns to this particular form. Nothing, just turn the derivative into a partial derivative with respect to J. Thus my delta Qj, my delta Q dot J term, this particular term vanishes. In this case, what I do is, if I add my minus V to the first term over here, so if you see, this is 0, right? This is 0. By adding a potential term on the first term, see T minus P, so if you multiply the derivative inside, by tau 2 by tau 2 will give me this, and my second derivative would give me 0. So like there is no loss of generality to put my minus V term onto that equation. So my equation will look something like this, because for Qj I define an equation like this, and it goes on to other side, I'll get an equation like this. Now I define a new function called Lagrangian, which is given by curly L. This is curly L. As a result, I represent my equation curly L, and the curly L is a function of Q, Q dot and T. Thus my Lagrangian, so my T minus P is a curly L, this is curly L. As a result, my equation will look like this. This is called as Lagrange's equation of motion. So we proved the Lagrange equation of motion by just hand waving. I'm really sorry for this kind of explanation, but I see no other choice, and honestly I don't even see this coming in your examination, but that's alright, that's how it goes. So I'll just take a careful approach next time for the next topic. See you in the next video.